In this problem, we're looking at whole grain consumption in the United States, and this is in millions of pounds, which is the output of this function right here. So C of t is the millions of pounds of whole grain consumed as a function of t, which is the year. Okay, so keeping in mind, anytime we're dealing with rates of change, which is what this class is all about, we want to think about what's the meaning of a rate of change in this equation. Well, since the output is millions of pounds and the input is year, our rate of change will have units that are millions of pounds per year. So any number that we come up with that's a rate of change will be in millions of pounds per year. This problem is going to demonstrate really that although we don't have to pick a bunch of points and find those slopes anymore, we have this nice simplified algebraic way of doing things. What it is going to demonstrate is still we have to do this 3 times, and this whole process, as you are starting to realize, can be a little bit lengthy. So it's good practice, but so this function tells us t is the number of years since 1999, and we want to know, according to this model, what is the predicted 2011 consumption of whole grain in the United States. Okay, now notice this doesn't say anything about rate of change. This just wants to know the consumption of whole grain in the United States in 2011. Okay, well, that's what the output of the function is for. So we really want to know how many pounds are consumed in 2011. Well, 2011 minus 1999, that represents 12 years. And so that's what we want to go in for the input. And let's plug this guy into our calculator. So we get 1.3 t squared plus 19.8 t plus 1848.8. Okay, and now what we'll do is we'll just go ahead and figure out vars, y vars, function y1 of 12, and this should give us the output, which is about 2273.6 million pounds. So that's a lot of pounds of whole grain that are estimated to be consumed in the year 2011, or have been consumed. Alternatively, if you like the table approach, you can go ahead and find 12 in your table by going to second graph, and that should still give you the same value of 2273.6. Okay, in part B, now we're being asked to find the rate of consumption in 1999. Now notice that this doesn't say find the average rate of change. That's the key in these problems, is it wants to know if you were to freeze time in 1999 and you were to ask consumption, how much are you increasing right now per year? And then consumption would tell you what it's increasing by at that point in time. So we're going to use the derivative to answer this question, because we want to know not just any old rate, but we want the instantaneous rate. That's what this class is all about. But it does not say average. It wants to know the rate at that moment. Okay, so by definition, 1999 would be 0. So a t value of 0. So we want to know c of 0 plus 8 minus c of 0 divided by 0 plus h minus 0. So change in output over change in input. And we're going to find the limit of this thing as the distance between these 2 points gets really, really infinitesimally close. So what we're going to do is we're going to first off find our c of 0. C of 0 is this guy evaluated with 0 plugged in. You can pretty quickly see, or go up to your table and see that when the input is 0, the output is 1848.8, which is really just the vertical intercept, the constant value in this equation. And then now we get to do the not so fun part, which is to go ahead and do C of 0 plus h, which requires us to take 1.3 times 0 plus h squared plus 19.8 times 0 plus h plus 1848.8. But if we're quick and we pay attention, we do notice that 0 plus h, what is 0 plus h? What happens if I add 0 to something? Well, I'm just left with the something, right? So I'm going to simplify this a little bit, and I'm just going to write 1.3, 0 plus h is h, got a squared, so notice no foiling is required here. 0 plus h is h, times 19.8 is 19.8h, plus 1848.8. Beautiful. So that saved us a lot of time, and now we can go ahead and plug things into our derivative formula. So limit as h goes to 0 of 1.3h squared. And by the way, you are going to notice some patterns, and don't assume those patterns always work. Like, you're probably looking at this and saying, oh gosh, well, this just looks like the same equation I started with, except it has h's in it. And that's only happening because it's 0 plus h. So the 0 really just disappears. And then plus 1848.8. But now that's basically my y2. Now I've got to subtract away that function evaluated at 0, which notice that the 1848 and the negative 1848 are going to cancel each other out, and so all my constants disappear from the top. Divided by 0 plus h minus 0, which of course that's just going to be h. If you want to think about the zeros canceling out, that works. And I have the limit as h goes to 0, 1.3h squared plus 19.8h divided by h. And I notice that there are no constants on the top, so I can factor out an h, because remember, my goal, if possible, is to get the h out of the denominator, so I can just go ahead and truly plug in h equals 0. So when I factor out an h, I get 1.3h plus 19.8, and I have that divided by h. So beautiful, I factored out an h, I can cancel it, and I get the limit as h becomes 0, 1.3h plus 19.8, and now I'm in the safe zone, so I can go ahead and plug in my apply my definition and just let h become 0, and I find out that the instantaneous rate of change in 1999 is 19.8. Well, what are the units? Well, it's a good thing we wrote them down. Millions of pounds per year. Really important to remember that this is not millions of pounds, this is millions of pounds per year, because we're working with a slope. So at that moment, if you were to do a snapshot in 1999, you'd find that production is projected to be increasing at 19.8 million pounds per year. So next year we would expect almost 20 million pounds more production than, by next year I mean the year 2000, as compared to 1999. So that's it for part B. At what rate was consumption changing in 2009? Explain the meaning of your answer with appropriate units. Okay, so in 2009, we just get to replicate this. So you kind of see how this is, you're like, oh gosh, well this is easier than, maybe not easier, but this is less time consuming than having to find all the individual slopes, but gosh, this is still kind of a pain. So now I have to do 2009, which is an input of 10. So compare two outputs that are separated by h horizontal units. Divide that by the change in the input, which again, notice that the 10 and the negative 10 are going to cancel. But I do need to figure out what C of 10 is. What is the actual production in 2010? Just go into my table here. Got this pulled up. 2176.8. And now I actually will have to do a little bit of work for C of 10 plus h. So my equation is 1.3 t squared. So I'm going to do 1.3, replace t with 10 plus h squared. So I have to back up here to figure out what the next value is. Plus 19.8 t, and in place of t I'm sticking 10 plus h, plus 1848.8. Okay, well, it doesn't really simplify just down to h in the parentheses here, so I have to FOIL. And if I FOIL 10 plus h squared, I get h squared plus 20h plus 100. I'll let you verify that. Plus 19.8 times 10 is 198. 19.8 times h is 19h. 19.8h. Plus 1848.8. Now I'm going to distribute my 1.3. So I get 1.3 h squared. 1.3 times 20 is going to be, I believe, 26 h. We can just double check it. We'll exit out of here and we'll do 20 times 1.3, which is 26. And then 100 times 1.3 is 130, plus 198, plus 19.8h, plus 1848.8. Obviously a lot of work to do this. So I'm going to combine like terms. I just got one h squared term. I've got 26h and I've got 19.8h. So 26 plus 19.8. 45.8. I've got three constants, 130, 198, 1848. I've got 130 plus 198 plus 1848.8, and that comes out to 2176.8. Well, that's it. That's all I can do for simplifying this. Now I get to plug it all back into this sucker right here, and I'm going to do that on the next page. So we have the limit as h approaches 0 of c of 10 plus h, which came out to 1.3h squared, plus 45.8h, plus 2176.8. So 2176.8. So that's c of 10 plus h. That's my output evaluated at 10 plus h. Minus, well, what did I get for c of 10? Well, look at that. I get 2176.8, which is just perfectly going to cancel out with my 2176.8 from this expression. And that's all going to be over, we canceled out the tens all over h. So that goes away, and I get limit as h goes to 0 of 1.3h squared plus 45.8h over h. And I get to go ahead and factor out an h because I can see that there's no constants left on top, and I'm about to cancel out the h, which is causing me my worries, and I'm going to be able to find the instantaneous rate of change. So that goes away, and I'm left with the limit as h is 0 of 1.3h plus 45.8. And now I'm in the clear. I can plug in 0 for h. I'm going to do that. Get 1.3 times 0 plus 45.8. And that means I have 45.8 million pounds per year as my rate of change. Whew, a lot of work. But I do have a number now, and I know what's happening in 2009. The production is projected to increase a whole lot more in that coming year. So is the difference between consumption change in 1999 and 2009 concerning? Why or why not? This is going to be up to you. What do you think? The rate of production, the rate of increase in the production has more than doubled, and that might be pretty concerning.